Hello, everyone. Welcome back. Today, we're going to go over section 3.2, which is the chain rule and the general power rule. So far, you've learned how to take the derivative of something that is raised to a power. So, for example, y equals x to the fifth. We know how to take the derivative of that. We use a power rule. Similarly, we have learned how to take the derivative of a function that looks like a product. So if you have a function that's f times g, two functions of x that are multiplied together, then you would use a product rule to take the derivative of that. We've also talked about the quotient rule, where if you have a function that is the division of two other functions, f divided by g, then you can use a derivative quotient rule to find the derivative of y. That was what you'd learn in section 3.1. So section 3.2 is a continuation of learning new derivative rules, and this time we're going to learn the chain rule. The chain rule typically applies to functions that are a result of composing them. So this applies to functions that are the composition of functions. So for example, a really quick visual example, if I take my y equals x to the fifth there, and I decide that I want to compose a function with that, say plug a function into x to the fifth, let's say that I had a second function g that is something like 1 over x. And I want to plug 1 over x into x to the fifth. Then my new function, which I might call something else, maybe z, is x to the fifth, but I'm composing g with it. I'm going to plug in 1 over x inside that so that it's no longer x to the fifth, it's 1 over x to the fifth. So this is an example of a composition of functions where one function is plugged into the other function. How would I take the derivative of something like that when it's no longer x to the fifth that I'm taking the derivative of? It's something inside the power that's not just x raised to the fifth power. That's where the chain rule comes in. So we're going to learn about the chain rule very broadly at the end of the section, but there is a subset rule under the chain rule that we focus a lot of time on in this section, and that's called the general power rule. The general power rule is under the umbrella of a chain rule, but it applies to the very specific case that you're taking the derivative of y equals something in parentheses raised to a power. So if you have something in parentheses raised to a power, you use a general power rule on that to take the derivative. And so that is what we learn in this section. If we scooch down here to the definitions, I want to look at part 2 real quick. This is the very broad chain rule that says that when you have a composition of two functions, say you have a function f right here, and I have a function g plugged into it, then the derivative rule that you use, called the chain rule, is you take the derivative of the outside function f prime, leave the inside alone, but then you have to multiply by the derivative of the inside function. Now this is a very symbolic way of writing it, but you take the derivative of the outside function, leaving the inside alone, multiply by the derivative of the inside. We will come back to this formula a bit towards the end of this section, and right now we'll just give it some lip service and say that the general power rule, which we're going to practice now first, is a subset of this broader chain rule. Now the general power rule, we're going to see very soon, is when you have some kind of constant we call c, where you have some function, this is where I have something raised to the power of r here. So if you have a constant times something raised to a power of r, then the derivative is given by c times r times that function, times that something, to the r minus 1 power, where you multiply by the derivative of the inside function. So all of the components of a power rule is here. C times r, x to the r minus 1, c times r, g to the r minus 1. But I have this extra little bit here that I've got to multiply. I've got to multiply by the derivative of g. So let's practice using this general power rule, which is a subset of the chain rule. I like to do a quick example here to kind of contrast the old power rule to the general power rule. If we have a function, y equals 2x to the fifth, we now know how to take the derivative of it. We can use the power rule to have c times r, 2 times 5, which is 10, x to the 5 minus 1. So you get 10x to the fourth is the derivative. And this we get by the power rule we learn in chapter 2. If I look to this side, I have y equals 2, 3x plus 1 to the fifth. I have here 2x to the fifth, but in this case, instead of 2x to the fifth, I have 2, 3x squared plus 1 to the fifth. It's got the general form, 2 something to the fifth, but now I have a composition. This 3x plus 1 is plugged in where the x was. So when this happens, this is a classic case of where I would need to use the general power rule to take the derivative. And fortunately, the general power rule is very similar to the actual one. The general power rule, I'm still going to do right here, where I did 2 times 5, which is 10, x to the 5 minus 1. I'm going to go 2 times 5, which is 10, but instead of x to the 2 minus 1, it's going to be this thing, the 3x squared plus 1, that I don't change. 2 times 5, x to the 5 minus 1, where x is my function here. The part that's new, that I have to remember not to forget, I have to multiply by the derivative of the inside function. I'm going to write f in here to abbreviate function. Derivative of the inside function. So the part that's in the parentheses is the inside function. 3x squared plus 1 is in the parentheses. It's inside the bigger function, 2x to the fifth. So it's the inside function. If I'm going to complete my general power rule, I have 10, 3x squared plus 1 to the 5 minus 1, which is 4. But then I have to multiply, and I'll use words again, by the derivative of the part in parentheses, the derivative of 3x squared plus 1. Copy down my last line. Now I know how to take the derivative of 3x squared. That's a power rule. 3 times 2 is 6. X to the 2 minus 1 is x to the 1, and the derivative of 1 is 0. So I end up with this format. I have 10x to the fourth on this side when it's a simple power rule, and I still have 10x to the fourth here, except now I have a function sitting in the place of where x was. And then I have this bit over here that I have to multiply, the derivative of the inside function. So the general power rule is a power rule, but it's using that broader chain rule to when you have something a little more complicated. It's all here in spirit though, power rule. 10, 3x plus 1 to the fourth times the derivative of the inside function. So we're going to get a bit of practice doing more examples like this. So let's do problem number 1. It's broken up into parts A, B, and C. Let's find the derivative for each given function. So all we're doing is finding the derivative mechanically. When I see this, and when you see any function, your first question is going to be, how do I take the derivative? Is it a product? Is it a quotient? This general form is something in parentheses to a power. So when you have this classic case of you have something in parentheses raised to a power, you should think, okay, I'm going to use the general power rule on this, which is the new one. So we have 4x squared plus 9x minus 3 to the third power cubed. And the way that the general power rule works, you do the power rule. You have c times r. C, the constant in front of this is 1. 1 times 3 is 3. But instead of x to the 3 minus 1 power, you leave the inside as it was. 4x squared plus 9x minus 3. 1 times 3 is 3. So we're doing a power rule here. C times r. 1 times 3 is 3. X to the 3 minus 1 power. But my x is this bit in parentheses. 4x squared plus 9x minus 3. The part we have to remember is now that we've done the power rule part, we have to multiply by the derivative of the inside function. That means the part that's in parentheses. The inside function here is 4x squared plus 9x minus 3. That doesn't mean I'm multiplying by 4x squared plus 9x minus 3. I have to multiply by the derivative of this thing. So I have to take the derivative of that and then multiply to be done. So my first part of this is 4x squared plus 9x minus 3 to the 2, right? There's my power rule part, times the derivative of 4x squared plus 9x minus 3, the derivative of the inside function. Now the derivative of 4x squared is 8x by a simple power rule. The derivative of 9x is 9, and the derivative of minus 3 is 0. So we end up here. And this is the derivative. We just use the general power rule to get it. In general, you can leave these unsimplified. Hawks will accept this as an answer. And if all we're doing is plugging numbers into something like this, it actually makes sense to go ahead and plug it in right here. Plug in a value for x, and you get a number out for your derivative, and it's a nice, quick result. If you want to make things fancy, you can go ahead and simplify this a little bit. A classic thing that might happen is you might move this term to the front here, to where that is 3 times 8x plus 9 times 4x squared plus 9x minus 3 squared. Now the way algebra works, I can't multiply that 3 into here because of that square, but I can multiply this 3 into this 8x and the 9 because the power on that thing is 1. 8 times 3 is 24. So in my first set of parentheses here, I'll have 24x plus 3 times 9 is 27 times the rest of this. Now again, you can stop here. This is the derivative. Slightly unsimplified, but it's good enough. This is acceptable. It's just fine. It might be beneficial in some cases to simplify, like if I'm setting my derivative equal to something, or if I'm trying to find the second derivative. So this is good enough if all we want is the derivative function, but if I want to do something with it algebraically, I may sometimes have to simplify. So for us here, I will show you some of these simplified down, just to show you how it's done. But this is good enough for most purposes. Now scooch down here to part B. I have 2x to the minus 2 plus 5x minus 3 to the 3/2 power. And again, the first thing you should always ask yourself is, what is the overall form of the function? Because the form of the function tells you what derivative rule are you going to use. So we go down through our list, right? Is this a product? Do I have two functions being multiplied here? No, I don't. It's just the one. And it's not a quotient either because I don't have one function being divided by the other. But what this is something in parentheses raised to a power. It's raised to the 3/2 power. So this is now one of these new cases where I would need to use this general power rule that we're learning today. Something in parentheses to a power. So for that, we say that my derivative, f prime, is, and we do the power rule. The coefficient in front of this term is 1, so we do c times r, 1 times 3/2, just 3/2, x to the 3/2 minus 1 power. See, this is the power rule, 1 times 3/2, 3/2, x to the 3/2 minus 1, but instead of x, it's this function that was sitting here the whole time, 2x to the minus 2 plus 5x minus 3. And so we're almost there. This is the power rule portion, but we have to remember this part of the chain rule, which is that I have to multiply by the derivative of whatever function's inside the parentheses. So in this case, it would be the derivative of 2x to the minus 2 plus 5x minus 3, the derivative of that. So I have to take the derivative of that part. Let's keep going. Now, as far as notation goes, we like to, because it's quicker, write the derivative as f prime, but just as a side note, you can also write the derivative as dy dx or df dx. do dy dx. In this Leibniz notation, both of these mean the derivative. We can switch back and forth, so don't be confused or intimidated when you see this notation referred to the derivative. I might switch to this as well the next time we do one of these. Anyway, here's my general power rule. Let's finish it up. I have 3/2 inside function 2x to the minus 2 plus 5x minus 3. 3/2 minus 1 is 1/2. And then I have to multiply by the derivative of the inside function, the derivative of 2x to the minus 2 plus 5x minus 3. For this one, I do a power rule. 2 times negative 2 is negative 4. X to the negative 2 minus 1 is negative 3. The derivative of 5x is 5, and the derivative of minus 3 is 0. So we get here, and we're done. This is my derivative function. So if I wanted to know what the derivative was at a particular x value, I could plug it in here and get it. But this is the derivative function at any x value. And while you could move this term up to the front and maybe multiply in the 3/2, since this is a fraction, it looks like if I tried to multiply it in here to simplify anything, I would just introduce more fractions and it would just kind of look ugly. So I'm just going to leave this as it is. I don't think it's beneficial to try to manipulate it or change things around any. We're just going to leave this one here. And again, as soon as you apply the derivative rule, this is your derivative, and that's an acceptable answer for the derivative. Simplifying things down is sometimes beneficial when you're doing more with it, but we're not. It's just asking for the derivative, and we go, okay, there it is. There you go. And move on. Our next practice problem here, part C, we have cube root of 5x cubed minus 4. Cube root. Now, I say this a lot in my classes, but roots shouldn't exist in calculus because we always have to convert roots to powers in order to do derivatives or calculus to them. So when you have a root in your function, we almost always need to transform it into its power equivalent, which is true here as well. If I want to take the derivative of something that's a root, I've got to convert that to a power. Now, cube root is the same as 1/3 power, so this changes to 5x cubed minus 4 to the 1/3 power. And if you didn't see it before, you can see it now as soon as you convert this to a power that, oh, this is this format of where I have something in parentheses raised to a power. When you have that happen, that is a classic case of having to use this general power rule we're learning today. And it'll always look like do a power rule on that, leaving the inside alone, and then multiply by the derivative of the inside. So let's do it. This function is called y, so it would be appropriate to write the derivative as y prime. In this case, I'm going to write it as dy dx, just to change the notation, but that just means the derivative. Dy dx equals, let's do our power rule. My coefficient here is 1 again, so you do c times r, 1 times 1/3 is 1/3. X to the 1/3 minus 1. Except our x is, this inside function, 5x cubed minus 4. So we leave the inside alone, just copy paste it and do the power rule to the outside part. The thing that we have to make sure not to forget is we have to now multiply by the derivative of the inside function. Multiply by the derivative of 5x cubed minus 4. So when I say inside function, I mean the part that's in the parentheses. I have to multiply by the derivative of that. So let's keep simplifying things down a little bit. I have 1/3 5x cubed minus 4. 1/3 minus 1 is negative 2/3. The derivative of 5x cubed when I do a power rule is 15x squared. And the derivative of minus 4 is 0. So I get here. And again, if all you're doing is finding the derivative, which we are, this is good enough. This is my derivative. You can leave it like this. You can input it into Hawks like this. This is the derivative. If we want to do something with it, which we're not in these problems, all they're asking for in the derivative, but if I did want to do something with it, you might move things around and try to simplify a little bit. In this case, we could bring this 15x squared up to the front. Let's move it to where it's 1/3 times 15x squared times the 5x cubed minus 4 to the negative 2/3. And then 1/3 times 15, or that is 15 divided by 3, is 5. So this gives me 5x squared times 5x cubed minus 4 to the negative 2/3. So we've simplified stuff down a little bit, but I actually can go one step further here. We are done taking the derivative, right? We accomplished that up here at this step, right up here. The rest of this is just making it look pretty. When I get down here, I notice that this is a negative power. And in general, algebraically, negative powers do technically belong in the derivative, in the denominator. So we have 5x squared. If I put this whole term back in the denominator to make the power positive, this becomes 5x squared over 5x cubed minus 4 to the positive 2/3 power. And this is a nice compact derivative here, simplified down all the way. There we go. So either one of these is acceptable. If it's asking for the derivative, you can stop here, and this is good enough. If we're doing something with it, like setting equal to 0, or trying to find another derivative with it called the second derivative, then it might be good to simplify it a little bit. So either one of these is fine. I just wanted to show you how it's done if you do want to simplify something further down. Our next problem here is part D. We have a function called g. It's x squared over cube root x squared plus 6. And as always, we have to look at our function and decide what derivative rule would apply to this. Like, what is its general form? When I look at this, it looks like a fraction to me. I have x squared divided by cube root of x squared plus 6. So this looks like a fraction. And I would approach this with a quotient rule because it looks like a fraction in its overall form, first and foremost. I do notice that I have a cube root in the bottom, cube root of x squared plus 6, but that will take care of itself later. What's its overall form? Most of all, looking at it straight away, it's a fraction. So I should start this with a quotient rule. Now let's recall from the last section that the quotient rule is if you have a function that is some function f divided by some function g, then the derivative is g times f prime minus f times g prime divided by the square of g. And so what I like to do is label the parts of my function. For a quotient rule, the numerator is always the function f, and the denominator is always the function g. So let's come over here to the side and make a list. F, the numerator, is x squared, and g, the denominator, is cube root of x squared plus 6. Now to finish my list for my quotient rule, I need to know f and g, and I need to know f prime and g prime in order to put them in my formula. So if f is x squared, let's find f prime, the derivative of f. The derivative of x squared is 2x when I use a power rule. But for g, when I look at it, that is the cube root of x squared plus 6. I mentioned it last time, but we don't like roots in calculus. So let's relabel this, where cube root is the 1/3 power. Now when I look at g, it's x squared plus 6 to the 1/3, Now it looks like that's something in parentheses to a power format. This is where, okay, now I've got to use the general power rule. I have a rule inside of a rule. I have a power rule, general power rule inside a quotient rule. So let's get started on this one. The coefficient in front of this is 1. So you do your power rule. 1 times 1/3 is 1/3. Leave the inside the same. X squared plus 6 to the 1/3 minus 1 power. There's our power rule. Then I have to remember to multiply by the derivative of the inside function. So let me write it again. Derivative of the part in parentheses over here. X squared plus 6. Let's finish up what g prime is. G prime is 1/3 x squared plus 6. 1/3 minus 1 is negative 2/3. And then the derivative of the inside function x squared plus 6 is 2x. So I get here. Now I am about to take everything in this list, f, f prime, g prime, and shove it into the quotient rule formula right here. I'm finding all the parts, what's f, what's g, what's f prime, what's g prime, so I can put it all in this formula. So this is going to get really ugly if all of those parts are log. It actually might be helpful here to go ahead and move this 2x to the front and simplify g prime down a little bit, just so it compacts everything, makes it look a little bit nicer. So 2 times 1/3 is 2/3. And this x is going to be moved to front. So I have 2/3 x times this part in parentheses, x squared plus 6 to the negative 2/3. This is my g prime, all of its glory. So I have f is x squared, f prime is 2x, we label g, and now we have g prime. I'm going to use all 4 of these parts to put them in my quotient rule formula, because again, the derivative of the whole original function is going to be a quotient rule. So let's bring this down here where I have a little more space. There's my formula. So write it out. Y prime is g. What's g? G was x squared plus 6 to the 1/3. G times f prime, which is 2x. G times f prime minus f. What's f? F was x squared times g prime. Now g prime is that ugly thing. So I'm going to use big parentheses here. 2/3 x squared plus 6 to the minus 2/3. And then all of this is divided by the square of g. So if that's g, I'm going to square that in the denominator here. So I have x squared plus 6 to the 1/3, and that gets squared. Now all of the parts are here according to my quotient rule. This is g, f prime, f, g prime, and that's the square of g. So it all lines up. And this looks pretty ugly. And this is where I'm going to say that we're going to mostly leave this alone without simplifying it further. We've done the derivative. As soon as you put it in the quotient rule formula, you're done. This is the derivative, as ugly looking as it is. And this is an acceptable answer for your homework. If I wanted to clean it up a tad, I could multiply this x squared times this x, make that x cubed, and I might move this 2x to the front. I also could bring out a greatest common factor of x squared plus 6 and x squared plus 6 to an appropriate power, but I'll leave that alone for now. My bottom, I could fix this one up real quick. If you have x squared plus 6 to the 1/3 squared, I have x squared plus 6 to the power of 1/3 to the power of 2. When you have a power raised to a power like this, the powers multiply. So this whole bottom will turn into x squared plus 6, 1/3 times 2, which is 2/3. So you might write that as 2/3 here instead. But this is good. You got the derivative. Now, the very last one that I want to do today is the derivative of this equation. But before we start this one, I would like to review a little bit about pulling out greatest common factors. What I want to do is not only show you how to take the derivative of that, but also I'm going to show you just the once how to simplify something that looks like it down all the way. So I'm going to get my side paper back and go off on a little bit of review first. So let's take these examples where we're back in college algebra and we say, for each of these expressions, factor out the greatest common factor from each one. So if we look at part 1, x squared plus x, and we want to factor out the greatest common factor, we have to figure out what the greatest common factor is. This is the expression x squared plus x. And so you have to think of what is an expression that you can divide evenly into both x squared and x. Another way you can think about it is, how many x's can I pull out? This is x squared, which means it has 2 x's. This is x to the first power, which means it has 1 x. If you're taking the equal amount of x's away from both terms, this one only has 1, that one has 2. So you can only pull out 1 because this one doesn't have 2 to give. You pull out the same number of x's from each term. So we decide that x divides evenly into both of those, and that's the highest you can get. So we're pulling out an x. And a lot of people can skip right to the end where we say x is factored out and it leaves me x plus 1 in the rest of it. X times x is x squared, x times 1 gives me the x back. So this is the factored version. I think most of the time in college algebra, we're comfortable going from here to here, just factoring out the x. But I did want to show the mechanics of what's happening in the middle, because that will actually come into play if we're simply simplifying down one of those ugly derivatives. So if I have x and I'm pulling it out, what's happening in the parentheses part is each of those terms that you had, the x squared and the x, is getting divided by the thing you're removing. So you place the x on the outside, it doesn't move, but on the inside of the parentheses, you have some division going on. You have to take x squared and divide it by that x you're removing, and you've got to take the x and divide it by the x you're removing. So in the interior part of parentheses, you've got to actually divide. What is x squared divided by x? Well, laws of exponents say that that simplifies down to x. What is x divided by x? That's 1. So you get this x plus 1 phenomenon happening here. X times x plus 1, and you get this. Let's keep that in mind as I do the rest of these. If we have x to the 5th plus x cubed, what is the greatest common factor between them? Well, how many x's does each have? This one has 5, this one has 3. Each of them have 3 that you can take out. So that is the greatest common factor is x cubed. That is also to say that x cubed divides into x to the 5th, and x cubed divides into x cubed. So what I'm going to do is pull out a factor, the greatest common factor of x cubed. And mechanically, what's happening then is as you're fixing the x cubed to the outside of the parentheses, what's happening inside the parentheses is those two objects, x to the 5th and x cubed, are getting divided by the thing that you're pulling out. So you affix the x cubed on the outside, and on the inside, you're dividing. X to the 5th divided by x cubed, laws of exponents say that's x to the 5 minus 3, which is x squared, and x cubed divided by itself is 1. So you get this factorization. Again, a lot of you probably could go from this to that without thinking about it. That's fine, that's great. But we will have to see the mechanics of how that works in the middle a little bit. So I wanted to refresh your memory on what's actually happening in there. Part 3. What if I have powers that are fractions? Now, those are a little harder to see. If I have x to the 3/2 plus x to the 1/2, and I say pull out the greatest common factor, you really got to think about what that means the greatest common factor is. It's the value of x that divides into both of the powers. But think about it when you had nice powers. What was the value of x you could pull out? It was always the lower of the two numbers. So between 2 and 1, what could you pull out? X to the 1. Between 5 and 3, what could you pull out? X to the 3. 3 is the lower of the two numbers. So when I have x to the 3/2 and x to the 1/2 is the lower value. So what I can pull out from both of them is x to the 1/2. It's the lower value numerically. So what we're going to do is this step in the middle, x to the 3/2 divided by x to the 1/2, and x to the 1/2 divided by x to the 1/2, and use our laws of exponents. The x to the 1/2 that you pulled out is stuck out front. It's fixed there. That's the whole idea. But inside the parentheses, I've got a division going on. X to the 3/2 divided by x to the 1/2. We have laws of exponents going here. This becomes x to the 3/2 minus 1/2. 3/2 minus 1/2 is 2/2, or 1. X to the 1/2 divided by x to the 1/2. Anything divided by itself is 1. So you get this sort of factorization, x to the 1/2 times x plus 1. The next one I want to look at, this is x to the -3 plus x to the -1. And again, the directions are pull out the greatest common factor. To which you go, oh goodness, how does that work with negative numbers? Well, remember that the greatest common factor, you pull out x to the lower value power. So if you have x to the -3 and x to the -1, which one of those powers is the lower number on a number line? If you think about it, -3 is more negative. It is lower in value than -1. It's to the left of -1 on a number line. So between x to the -3 and x to the -1, x to the -3 is the lower value power. That has the lowest value power. So what I can pull out is actually x to the -3, since that's technically the lower value number. So this is where I really need to use this intermediate step of dividing. If I'm pulling out x to the -3, what's happening is both of those are getting divided by x to the -3. X to the -3 divided by x to the -3, and x to the -1 divided by x to the -3. We just kind of have to trust the process here and hope we get a good, hope we remember our laws of exponents. X to the -3 times x to the -3 divided by itself is 1. So that's nice. And then here, what happens here, laws of exponents say this is x to the -1 minus -3. X to the -1 minus -3, which becomes x to the -1 plus 3, which is x to the 2. So when you factor this, it's x to the -3 outside of 1 plus x squared as a factorization. This is a good review because we will see some negative powers on some of our terms when we go to simplify more complicated derivatives. So let's come back here to our derivative problem. I have y equals 2x plus 7 cubed times 3x plus 1 to the -4. And the directions are find the derivative. And as soon as we're done doing the derivative rule, I'm going to say, okay, we're done. This is an acceptable answer. This is good enough for your homework. You're fine. But then I'm going to go on to say, okay, now that this is the derivative, let's simplify it down a little bit just so we can see how it's done. So here we go. When I look at this thing, the first question you always have to ask yourself is, what is the overall form of this function? What derivative rule do I need to start with based off of how it looks? When I see this thing, this is 2x plus 7 cubed times 3x plus 1 to the -4. This is a multiplication of two functions. This is going to require a product rule because this function y is a product of two smaller functions. 2x plus 7 cubed times 3x plus 1 to the negative 4. You include the power on that, on both of those. So because it's a product of two functions, I would have to use a product rule to take the derivative. So this is where I like to make a list. What's my first function being multiplied? That's the 2x plus 7 cubed. What is the second function being multiplied? That is 3x plus 1 to the negative 4. We call those separately f and g. As part of my product rule, which we may recall, product rule is f times g prime plus g times f prime. So I'll write this as the product rule there. That's the formula we're going to use for taking the derivative. So I have to label f times g prime plus g times f prime. There we go. I have to label what f is, I have to label what g is, and then I have to take their derivatives because I need f prime and g prime. So if this is f, what is f prime? And this is where I have to ask myself again, okay, how do I take the derivative of that? Well, this is something in parentheses to a power. So this is where my general power rule is going to come in. So I have to do this new derivative rule we're learning today on this one. So let's do our general power rule. 1 times 3 is 3 times 2x plus 7 to the 3 minus 1 power. There's my power rule. Make sure you leave the inside alone. It's exactly the same. But then you have to multiply by the derivative of the inside function, right? So I'm taking the derivative of 2x plus 7. Derivative of 2x plus 7 is 2. So my f prime, if you allow me to simplify it a little bit, I have 3 times 2 here, which is 6 to the 2x plus 7 squared. That's my f prime that I'm going to use. Then I come down here to my second part of this big function. It's g. And as part of my product rule, I need to know g prime in order to use the product rule formula. So again, I'm faced with something in parentheses here to a power, where I need to use the general power rule, our new rule, in order to get it done. My coefficient is 1, so you do 1 times negative 4, which is negative 4. Leave the inside alone. It's 3x plus 1 to the negative 4 minus 1. Negative 4 minus 1 is negative 5. Now remember, as part of the general power rule, you've got to multiply by the derivative of the inside function. The inside function is 3x plus 1. So you're going to multiply by the derivative of 3x plus 1. So I get negative 4, 3x plus 1 to the negative 5, times the derivative of 3x plus 1, which is 3. Here, if you let me clean it up a little bit, negative 4 times 3 is negative 12. And I have negative 12 outside of 3x plus 1 to the minus 5. You can multiply the negative 4 and the 3 together because I don't have a power on the inside, but you can't take, for example, this negative 12 and multiply it in there because of the negative 5th power. But I can do stuff on the outside of this parentheses here. This is my g prime that I'm going to use for my product rule formula. So I've labeled all my parts of my product rule. I've got f, I've got f prime, I've got g, and I've got g prime. Those are my pieces. And I'm going to take every one of those and I'm going to pop it in here to this product rule formula. And as soon as I write it in that product rule order, you will have your derivative. Let me separate this. Y prime is f first. What is f? F is that. Copy it down. 2x plus 7 cubed times g prime. G prime's down here. Negative 12 times 3x plus 1 to the negative 5th. So f times g prime plus g. Here's g. 3x plus 1 to the minus 4. Times f prime, which is right there. It's a bit of a mouthful there. But this is the derivative. As soon as you write it in the product rule order formula, you are done. So this is where I will stop and say, okay, this is the derivative. It's good enough. If you're plugging this into your homework, you can plug this in. Might take you a while to type it, but there it is. There's a derivative. You're good. You're done. So if you want to plug in a number into this, if it asks for, say, the derivative at x equal 2, you'd take and plug in an x value here and not worry about simplifying it. But just for the sake of seeing it, let's pretend like I wanted to simplify this down because I'm about to set the derivative equal to 0. So yes, this is the derivative. Yes, this is good enough to stop if all we want is the derivative function. We're good to stop here. And as far as the question's concerned, we are done. But just for letting me show you, let's continue on just so I can show you how it's done. How do we simplify this down a little bit? Well, first things first, I'm going to take these little constants here, minus 12, and I'm going to move that to the front because it's the only one here that doesn't have a power on it. That's got a cube on it, that's a minus 5, but I have this constant hanging out front. So it's good form to move those to the front just so we don't lose track of them. I have negative 12 times 2x plus 7 cubed times 3x plus 1 to the minus 5 plus, same goes for the 6. It's kind of hanging out by itself. I'm going to move it to the front where this becomes 6 times 3x plus 1 to the minus 4 times 2x plus 7 squared. Now this is my derivative. This is y prime, right? And so I have two terms here. 1, 2. And in those two terms, I have common factors. I see a 2x plus 7 here and here, to different powers, but a 2x plus 7 in parentheses in both places. And I have a 3x plus 1 to a power here and here, just with different powers. So what I can try to do is pull out the greatest common factor involving 2x plus 7 and 3x plus 1 to an appropriate power. So this is where we have to kind of dissect this a little bit. If I look at first both of these terms, and I just look at the 2x plus 7, this is 2x plus 7 cubed, that's 2x plus 7 squared. So just between those, what is the greatest common factor between them? This has a cube, this has a square, so I can pull out a 2x plus 7 squared. This would be similar to me asking, what is the greatest common factor between x cubed plus x squared? It would be x squared. It's just instead of having x's, I have 2x plus 7's. X cubed and x squared. 2x plus 7 cubed, 2x plus 7 squared. I can pull out a 2x plus 7 squared. So let's do that. Let's say I'm going to take a 2x plus 7 squared and pull it out. And that means that this term and this term are going to get divided by what I'm removing. Same as what I was doing on our sample page there, pulling out the greatest common factor. But then I also see 3x plus 1 in both places. I have more greatest common factor to build. This is 3x plus 1 to the minus 5. This is 3x plus 1 to the negative 4. Which one of those powers is the greatest common factor? Remember, when you had the negative powers, it was kind of backwards. Between 2x plus 7 cubed and 2x plus 7 squared, you can pull out 2x plus 7 squared because it's the lower of the two powers. Between 3x plus 1 to the negative 5 and 3x plus 1 to the negative 4, which is the lower of the two powers, it's the negative 5. So I can also pull out 3x plus 1 to the negative 5th power. And that means that I'm going to write a big set of brackets here. In my parentheses, this term is going to get divided by that, and that term is going to get divided by that. And there's going to be some simplification going on. So I'm going to bring this down where I have a little more space so I can show this being done. I've got 2x plus 7 squared. times 3x plus 1 to the minus 5 that I'm going to pull out as my greatest common factor. And actually, if I want to be particular about it, I have a negative 12 here and a 6 there. Between those constants, I can actually pull out a 6. Negative 12 and 6. So I'm going to make that a addition to my greatest common factor here. I can pull out a 6, I can pull out a 2x plus 7 squared, and I can pull out a 3x plus 1 to negative 5. And in my big brackets here are these two terms, the original terms, that are going to get divided by that thing. So it's going to look a little bit like a mess in here. First term gets divided by that. So let's write our first term here. Minus 12, 2x plus 7 cubed, 3x plus 1 to the negative 5. That's my first term. It's getting divided by greatest common factor. Which is that thing. All right, that takes care of the first term. Big plus sign, which is that plus sign, plus second term. That thing is going to get divided by greatest common factor. So we write that part out. First term right here. Divided by greatest common factor. Now this looks absolutely terrible and ugly, admittedly, but fortunately, nice things start happening here. So this term, whole term that I have underlined here is getting divided by greatest common factor, and so is this one. And we're going to see what we're going to be left with here. So my greatest common factor is going to stay outside the parentheses. That's the whole point of bringing the greatest common factor out. It just kind of hangs out up front. Now, inside my parentheses or my big brackets here, I have some laws of exponents going on. Negative 12 divided by 6 is negative 2. I'm going to write that as negative 2. And I have 2x plus 7 cubed divided by 2x plus 7 squared. Laws of exponents say you have 2x plus 7 to the 3 minus 2 power. So that should be 2x plus 7 to the 3 minus 2, which is 1 power. And as we see, 3x plus 1 to the minus 5 divided by 3x plus 1 to the negative 5. Those actually cancel. Anything divided by itself is 1. So that big old ugly mess just simplifies down into that. 2x plus 7 to the first power. That's kind of nice. Big plus sign. Now let's take care of this mess over here, the second term. 6 divided by 6 is 1, so they cancel each other. 2x plus 7 squared divided by 2x plus 7 squared, they cancel each other. 3x plus 1 to the negative 4 divided by 3x plus 1 to the negative 5. Now those are different powers, so we don't cancel them. But what we do have here, let me write this off to the side, is 3x plus 1 to the minus 4 minus negative 5, right? Laws of exponents. Negative 4 minus negative 5 becomes negative 4 plus 5. Negative 4 plus 5 is 1. So this whole mess becomes 3x plus 1 to the 1, first power. Now that looks a lot nicer in there. Let's simplify it down a little bit more. The part in big parentheses, I can take this negative 2 and multiply it in. Why not? And then this is just plus 3x plus 1. So this greatest common factor, still just hanging out up front. We're not doing anything with it. Inside the parentheses, I've got negative 2 times 2x is minus 4x. Negative 2 times 7 is minus 14. And on this side, I have plus 3x plus 1. Last step. Let's combine some like terms here. I've got minus 4x plus 3x and minus 14 plus 1. Let's combine those. Minus 4x plus 3x is minus 1x, and negative 14 plus 1 is negative 13. And so finally, we have a simplified derivative. If we kind of zoom out, see how far we've come. All the way back here, we said, this is the derivative, and that's good enough for our purposes if all we want is a derivative function. So for you guys, you probably should stop here. If we ever wanted to do something else with it, though, like in future sections, you might simplify it down using these types of steps, and then we see something like this, where instead of having two terms that are multiplied together, where I had one big term plus one big term, what I have here is one big factorization. 6 times 2x plus 7 squared times 3x plus 1 to the minus 5 times negative x minus 13. This is a nice, succinct, simplified derivative that might be useful a little further down the road when we learn more applications of our derivatives. This is my simplified derivative. Now again, for you all, you can stop here. I just wanted to show you how you would simplify if you ever needed to. These are the types of tricks you could use here when you get something that looks like this. Now this is all I wanted to show in this video. This section is not over though, so please pick up on the next video where we do some more examples where I don't go through the whole simplifying thing and finish up this section. See you next time.